like 2 times that match the most people. And then hope that some other teacher can join us.
All right.
But if
So
not, at least we have everybody.
I'm curious how this is going to work out, because your slides got finished at about 2 a.m. I think I was like, I don't know if we're going to be doing that card. So.
This is a story I keep hearing on repeat. So how often do you actually sleep?
Well, I sleep every day. It's just for how long is the question.
Yeah, but how long is the perfect amount?
The perfect amount is about 11 hours.
I second that.
Yeah. There was a time when I was in grad school that I just didn't really have a schedule, and I just slept however long I wanted to sleep, which was a little hard on my wife at the time, because she had to go to work and everything, and I was like, my schedule, I would sleep for 11 hours, and then I would stay awake for maybe 15 hours, and then I'd sleep for another 11 hours, and I slowly rotated around the clock, so that my days were like 26 hours long. But my natural schedule apparently is the same as the time, the length of the day on Mars.
They've done studies on that. I think all of them
Is this something
like that.
Huh?
They've done studies on that, where they put people in like a sensory deprivation chamber or like underground with no like natural sunlight or anything,
Yeah,
and it's made about 25 to 26 hours.
Maybe all humans are from Mars. That's or maybe the day length has changed.
It's speeding up a little bit as the moon slowly goes.
Anyway, here we are. It's the 20th. A couple of reminders. You know, this is next Friday now, the 27th. And that paper should have a bibliography in it. And I'm thinking this is a little bit of a late thing to say to you, but if you haven't figured out what's up with the math in your particular movie, because your emphasis should be on the mathematical content that's in there, talk to me. Come and see me in office hours or after class or something. Because that's the reason you need a bibliography. I would send you to some sources, or you can find sources by Google Scholar or use the libraries resources. I want to investigate the mathematical issues on there, and then find other people that have done reviews so that you can see what they thought about the math issues. The people were talking about the Putnam exam earlier, the Putnam exam prep sessions are on Fridays, and it's a good time. We have so much fun. What was that?
Yeah, it's fun. Plus free pizza.
Free pizza. Dr. Gingrich is always entertaining. I'm going to talk about the pigeonhole principle today.
Okay.
You guys know the pigeonhole principle?
It involves pigeons.
Well, not really, but you know, that's it's if you have like, okay, how many people are in the room? 13. I can guarantee 2 of you have the same astrological sign.
Nah.
Maybe.
Absolutely. There's 13 of you. How many signs are there?
We don't each have to. We can each be the same sign.
He said
At least 2 of you have the same sign.
He didn't say it could be more than 2. He said at least 2.
That's the pigeonhole principle. If you have 367 people in a room, you know some of them were born on the same day of the month. In fact, there's some weirdness. Like, if you look at all the people in New York City, there's more people than there are possible human hairs on their head. So there have to be 2 New Yorkers with the same number of hairs on their head.
I was going to say that's silly, but that's actually kind of interesting.
That's sort of, I mean, you never figure out who they are. And it probably changes from day to day. You know, one hair falls out, falls in.
Is that from the street?
Yeah, that's a discrete math problem. And it's amazing how many problems that seem impossible at first come down to just figure out what are the pigeons and what are the pigeonholes. You know, what do I have too many of to fit into these categories? And then that having too many implies some fact that you're after. Those of you who are in 250, a couple of you are in 250. You are? Yeah. That's something that you'll see sort of towards the end of the courses. Sort of discrete math arguments, pigeonhole principles. Anyway, plug for that. But the main thing is that if you have been kind of on the fence whether you were thinking of taking the test, it's today is the deadline for actually signing up. And, just talk to Dr. G and he'll add you to the list. Okay. We're still talking about Leonardo of Pisa, this sculpture in the city of Pisa. I don't know how accurate that is. That's his real name, but everybody knows him as Fibonacci. And I mentioned this in class Monday, right? His name is supposed to be a contraction of Filius Fibonacci, which means son of Fibonacci, or child of Fibonacci. I mean, really it means child, but it's got the male inflection on it, so to treat it as son is maybe a little bit sticking too close to the literal translation. I think it's figured out that it's child of Fibonacci. And that's not his father's name, so to think that it's... Anyway, we talked about the Fibonacci sequence last time, and I pointed out that it's close to being a geometric sequence. It's not exactly, but it's close. But if it were a geometric sequence, just pretend for a moment, then all the entries in the Fibonacci sequence would be powers of some common ratio. And then the common ratio powers, like the n plus first and the nth and the n minus first, those would be the terms of the sequence. And so they'd have to satisfy that relationship that the sequence satisfies. The next guy is the sum of the two that come before it. The n plus first is the sum of the n and the n minus first. But those aren't just indices anymore, right? I'm pretending that those are the powers of R. Right? So those are powers, not just indices, and we can divide. So we do need to make an assumption. R to the n minus 1 probably isn't 0, but are any of the Fibonacci numbers 0? Nope. Wow. The negative first one probably is 0, but I mean we usually don't go in that direction anyway. If you're up in the sequence somewhere, you're talking about non-zero things. So divide it out, and you get this. R squared is equal to R plus 1. And that's a quadratic. And then, right through the solution, you get those. 1 plus root 5 over 2, and 1 minus root 5 over 2. The form of those things looks like it came out of the quadratic formula, doesn't it? These numbers are related to one another. This is the golden ratio. Do you say phi or phi?
I say phi, but I'm always not saying wrong.
A little interesting point. One of the math professors in our department, Dr. Diamantis, is from Greece. Probably tell from the name. And she actually does study abroad stuff. Takes people to Greece on trips every year. It's really cool. And she told me that it's actually pronounced phi in Greece. So there's that. But you know that pi is also pronounced p. Because it sounds dirty and it's just funny, right? Yeah. But actually our letter P sounds like that too, so I don't know why that's amusing to me. Somehow it is. Yeah, so what is that other number? 1 minus root 5 over 2. I just want to show you this calculation. Take the two numbers here and multiply them. So the fractional part is going to give us a 1/4. I'm just going to pull that out in front. Question. We have 1 plus root 5 times 1 minus root 5. If you've done complex numbers, this is much like the conjugate with complex numbers, although this is what's called an algebraic conjugate. And that, in fact, the things that come out of the quadratic formula are always algebraic conjugates. They look like 1 plus a radical and 1 minus a radical. And it's the same radical, which is nice because when you expand this by, use FOIL for expanding, or distribute, whatever, you're going to see terms that kill each other off. You'll have first times first, sure, but outer times outer is minus root 5, inner times inner is plus root 5, and so those cancel, and you end up with 1/4 of 1 minus 5 root 5 squared. Yeah, I'm not going to write that. I was about to write root 5 squared. That would be silly. 1 minus 5, because it's root 5 times root 5. So that's negative 4, and that's 1/4. This is negative 1. So what do you conclude about these numbers? They are negative reciprocals. That is, phi, or phi, I'm still doing it wrong, is 1 plus root 5 over 2, and the negative of phi inverse is 1 minus 5. So which to use? Which should we use? Well, if we think we're going to try to get a formula for the Fibonacci numbers, I thought I'd give you them as decimals. And I already pointed out they're negative reciprocals. Do you think you should have this negative number of various powers to get the Fibonacci numbers?
Isn't the other one, I've seen this in 2 forms, isn't it root 5 minus 1?
If you, so the negative of that would be root 5 minus 1 over 2, and then you were just talking about the reciprocal. Maybe that's what you said.
Because I've seen some.
If you switch the order in a subtraction thing, it just changes the sign. So I think it's pretty clear that we want the positive number and take powers of it. But the powers of 1.618 aren't even going to be whole numbers. And furthermore, we saw something when we kind of looked at the Fibonacci sequence that it had a little bit of wiggling in it. Sometimes it went up more, sometimes less. You know, there was a back and forth going on there. So let me just, I have a bullet here to point out what happens with powers of these two things. If I have a positive number and I keep taking higher and higher powers of it, that's an increasing function, for sure. But if I take higher and higher powers of a negative number, what does that do? Well, anytime you've got an even power, you'll have an even number of minus signs in that product. Right? And so it can end up being positive. So this is how you get alternating series. Remember alternating series in Calc 2? If you haven't done Calc 2, it's just thinking about how many minus signs there are in a continuing expansion. So yeah, the powers of the negative 0.618 alternate back and forth. But how big are they getting? As we go to higher and higher powers, I mean, the sign goes negative, positive, but the size of the number is a higher and higher power of just the absolute value there, 0.618. That's a number smaller than 1. What happens with its powers as you go large?
Well, doesn't it go to 0?
They go to 0. So the two geometric series that we potentially have do something like this. One gets alternating back and forth, but approaching 0, and the other just climbs. And the weird thing about the Fibonacci sequence that we're trying to come up with a formula for is it has elements of both of these phenomena in it. The Fibonacci sequence actually does something like this. It goes low, then it goes high. Lower than a geometric series would, then higher than a geometric series would, then lower, then higher. So this is phi to the n. This is negative 1 over phi to the n. And the one that we're after, fn, appears to be a combination of those two things. I mean, that at least it's got that here.
What did I miss? Why is it called the graphic problem?
Don't hear about the breeding of rabbits.
Incestuous rabbits.
You were out that day? You start with a pair of bunnies and their babies, and then a month later they grow up and become big bunnies. I'm not going to draw ears for you. We did ears last time. Imagine the ears.
I'm sorry, I missed something on Wednesday, I guess.
Then once they're adults, once they're adults, they have sex, and a month later they have babies. So a month later you have this picture of the original bunnies are adults, then they have sex, then they have babies, right? And then from there on out, the pair of bunnies keeps having babies. So the next month, these guys will have new babies, but their babies will have grown up.
And rabbits are.
Okay, I got it.
Right? And so what ends up happening is that any pair that was alive in the previous month gives you babies in the next month. And anybody who was alive 2 months ago, whether they were babies or not, gives you adults in the next month. So it's the problem that was really stated in Fibonacci's book about how to use an abacus, and it really was just a practice on using an abacus, was to figure out how many bunnies you have after 12 months.
Wednesday and not Monday, 'cause I really did pay attention on Wednesday.
Monday.
Okay.
Wait,
They
this is
said,
a problem.
somebody said Wednesday, I was like,
No.
that's why.
We
I missed it.
started talking about this on Wednesday, about the actual Fibonacci sequence.
I was being
Did I mention
confused
that I
at
gave
this
you new
season.
homework, by the way? I forgot to say.
You posted it on Blackboard.
I posted it on Blackboard. You should have got a notice from Blackboard, but I should have said something. That should have been in the reminders. Because there's two sections in the stuff about Fibonacci. There's one section that's about Fibonacci kind of generally, some of the problems he put in his Liber Quadratorum and his Liber Abaci. And then there's stuff about this, about the Fibonacci sequence, which there are two subsections. That's why it reminded me. So, yeah, the point is maybe we can take a combination of powers of these things and get a Fibonacci sequence. And so here's the question. There's no question mark in that, but it's a question. Is it possible to find a linear combination? So who knows what linear combination? Who's been in linear algebra? Or is in it now? What's a linear combination of these powers look like? It's something times the one plus something times the other. Say again? There are, it's in linear algebra, but you know, there's more things that are vectors than you might imagine. You can think of that as a vector. Unfortunately, it's an infinitely wrong vector. It's got one for n is 1, one for n is 2, one is it's got a lot of entries, but it's still can be thought of as okay, just treat it all as one vector. So we've got a number times a vector plus a number times a vector. That's what linear combinations are. But you know, what is it really? I've just got numbers out in front of those things, and I want to figure out what they are. So can we? Well, yeah, of course we can, because we wouldn't be telling you if we could. The point is, we know some of the values of the Fibonacci numbers. In fact, several of them are quite easy. Like when n is 0, what's the Fibonacci of the 0th Fibonacci number? 0. That's when you first get your baby bunnies. It's 1. And the first Fibonacci number is 1 also. So we'll use that. I think I put it on the slide. Yeah, we've got a small 2x2 system of equations, and this is it. The first one comes from thinking about when n is 0. If n is 0, whatever this horrible looking thing is to the 0 power is still 1. And same for this one. Anything to the 0 power is 1. So then it looks like alpha times 1 plus beta times 1 is equal to the 0th Fibonacci number. Saying alpha plus beta is 1. The other one, not so easy. It says that when we put the first power in, when n is 1, we also get the first Fibonacci number. That was the 0th one. These two ones are actually different Fibonacci numbers, but they're both 1s. We'll have alpha times phi plus beta times negative 1 over phi. That's equal to 1 too. That's two equations and two unknowns. Shouldn't have a solution, right? When would it not have a solution? You know? I mean, we've done that in like pre-cal. Is there circumstances when they would not have a solution?
Same slope but offset by different values?
Yeah. And can you tell what the slopes of these lines are?
They're different.
They're definitely different, yeah. This guy, the coefficients of alpha and beta are both the same, and this guy, the coefficients of alpha and beta are both different. Clearly different slopes. If you try to solve for, we'll put it in the form beta equals m alpha plus b, you get different apps. Or I'm supposed to erase it. Alright, so I'm going to use the method of substitution. We'll take the first equation and solve it for one of the variables. Which variable do you like to work with?
Alpha or betas, because I like betas.
So if I solve it for beta, we'll be getting rid of betas. If I'm going to satisfy you, I want to solve it for alpha.
Oh, that's what I meant, because I'm alpha.
Oh, all right. You don't like alpha? Alpha equals 1 minus beta. Okay, that's just re-expressing the first one. Now we can get rid of alpha in this one, and it becomes 1 minus beta times 1 plus root 5 over 2 plus beta. That doesn't, I just gotta do that over. Beta came out funny. Plus beta times 1 minus root 5 over 2.
Equals is 1.
Yeah, it can't just be sitting there by itself, can it? I better have it, something on the right hand side.
Isn't that just?
I was just thinking, can we possibly clear the fractions? The fractions are making me unhappy. I just double both sides? Okay. So then we have 1 minus beta times 1 plus root 5 plus beta times 1 minus root 5
Equals 2.
equals 2. Awesome. I'm going to have lots of stuff with betas in it and some numbers in it in there, and you know it's just algebra, so I'm going to start cranking. Did you look at that?
I was just wondering, did you just distribute?
Yeah, I think I got to distribute. Well, this expression I'm going to go ahead and FOIL right here. 1 times 1 is 1. Outer times outer is root 5. Inner times inner is minus beta. And last times last is negative root 5 beta. And this one is plain distribution. We have plus beta and minus beta times root 5. All is equal to 2. You're right, there's a minus beta here and a plus beta there. And how about the two things that are left that have beta, both are negative root 5 beta. And what are the pure numbers? It's 1 plus root 5. I'm going to take them to the other side. So there's going to be 2 minus 1 plus root 5. What's left on this side is negative 2 root 5 beta. I think I'm going to be able to just do one last thing here. Let's say negative 2 root 5 times beta is equal to minus 1. So it's 1. And then minus root 5. I'm unhappy with the minus sign on the left. So we can fix that. Make both sides negative. And finally, I just divide both sides by the 2 root 5. So beta is equal to root 5 minus 1 over twice root 5.
You can simplify that even more.
I would be happy with that answer, but a purist will say you may not have an a radical in the bottom. So how do you get rid of that radical in the bottom? Multiply by root 5. Top and bottom. And then when I multiply that by root 5, I'll end up with a 10 downstairs. Can I do more? Distributing that guy, we get 5 minus root 5 over 10. Actually, I was happier when I just had a 2 in the bottom. I've done something silly. I should have just divide both sides by root 5 here.
Yeah.
I'm just the history teacher. I don't know nothing about solving no equations. Right? Root 5, I should have, let me just recopy this step where I went haywire. It's root 5 minus 1 over twice root 5. Yeah. So what I should have done is divided top and bottom by root 5. And then I have 1 minus 1 over root 5 divided by 2. That's a little easier. Because what is happening here? That's the reciprocal. No, that's the reciprocal root 5. Can you make that better?
So now rationalize that denominator in the top.
So just make that 5, root 5 over 5.
Yeah. Wait.
I'm just so unhappy with this form for the answer. I don't know.
Change the radical into exponents.
Yeah, so that's 5 to the negative 1/2 power there.
5 to the
You know what? I'm just going to say, screw this rationalizing denominator stuff. Really, that's fine. I can deal with that expression. Right? That's beta. Okay, we just found beta. What's alpha? It's been erased now. But alpha is 1 minus beta. Okay, they add to 1. So alpha is 1 minus beta grade. That we're going to need to write it as 2 over root 5 over 2 over root 5, because that's 1, right? Minus beta, which is root 5 minus 1 over 2 root 5. Now can we subtract? It's 2 of these root 5s minus 1 of these root 5s, and 1 of them, and then plus 1. So it's root 5 plus 1 over 2 root 5. And this guy, that's alpha.
Very similar to the things that would be multiplied to.
Yeah, they do, right? But those are going to just be numbers, not powers. They won't have exponents on them. All right, so yeah, let's put this together now. I don't think I did that on the slide. Alpha is this expression: root 5 plus 1 over twice root 5 times this next thing is actually phi raised to the n power. 1 plus root 5. Plus, the other one, I just said alpha, right? Yeah, the other one is beta, root 5 minus 1 over 2 root 5 times, this is phi's negative reciprocal. Some people call that phi bar. Anyway, it's 1 minus root 5 over 2. That's Fibonacci sequence. Not nice so much, but do remember that this is just some number. If you were doing this on a computer, you get it as a decimal. Right? That's some number. This is really just, if I say it without referring to the actual expressions there with radicals, this is alpha times phi to the n plus beta times phi bar. It's really quite a simple form for a formula. The numbers are ugly, but the shape of the formula is not. Okay, so I think that's where I run out of slides. That's where I run out of slides. I actually wanted to talk about, I was sort of tossing up two different people. René Descartes. You like René Descartes?
It's a philosophy,
Yeah. He's more famous as a philosopher in a sense than as a mathematician, but I think that's unfortunate because his philosophy is quite naive.
Yeah, he tells you that.
But his math was fundamental. His math was really huge. The other person I thought we might talk about next is John Napier. or John Newton. So, yeah, logarithms. He's the guy that invented logarithms. You think, what's cooler now, the Cartesian plane or logarithms? Well, I'll leave it up to you which one you're talking about.
Logarithms.
You like logarithms? I'm seeing, I would have thought everybody go, yeah, Descartes. All right.
I hate Descartes with a fire passion.
No,
Why do you
like
hate Descartes?
Descartes tells you like that your name's not your name, and that you're supposed to examine you, that your name.
Well, Plato said that stuff.
Descartes has one good thing. I think therefore I am.
Yeah.
He then tried to use that as the foundation to build everything else, but he was just wrong about everything else. That's the one thing he was right about philosophy.
Why?
So, Aristotle, right? I think therefore I am.
Right. Well,
Is
that's-
patently false. Does this chair not exist?
Is that chair? It's your name, your name.
I believe that chair's got some sort of actual existence, and it doesn't think. I'm
It
pretty
could be
sure-
How do you know it doesn't think?
I think it doesn't think.
Well, that's the
So
thing.
I got to tell you the Descartes joke, and then we'll move on. So you've all heard this phrase, I think, therefore I am. So Descartes is sitting in a cafe in Paris, having a little coffee and croissant, and the waiter comes up to him and says, in a ridiculous French accent, says, Monsieur Descartes, would you like another coffee? And Descartes goes, I think not, and poof, disappears. I really thought you were going to like that.
What?
I think not, he says. Work with me on this, guys. Come on, that's funny.
That's not really funny.
Don't forget, he grades our papers. Great work!
I remember, but it's not thinking. It's not the same. Yeah.
So we'll talk about Napier. Okay. Have you ever heard the expression to throw the book at someone? What does it mean?
Is it kind of
Yeah, but it actually comes from the military. The military used to have a book that was this big fat book for calculating trajectories of shooting, cannonballs at other people. And when somebody did something stupid, the artillery officer would chuck the book at them, literally. And you got hit with this 3-pound book. It hurt. So, and the book was kind of a problematic item on a battlefield. Because there are lots of stories about people being shot and having to have the book in their pocket, right? Have their lives saved by the book. Other people would get shot and it would just spray on the book, right? The book would get muddy and gross and become unusable. And plus, it wasn't easy to use in the first place. I mean, other people are shooting at you. They're aiming their cannons at you, and you want to get your cannon aimed at them real quick. And you're sitting there going, where the hell is that page in the book, right? You don't want to be doing that. So Napier came up with something he called Napier's bones. And these were a tool for doing calculation. Basically, the book was about being able to multiply and divide, and I guess you need to square things too, so that's multiplication as well. To calculate the trajectory of a ballistic projectile. They knew how to do that stuff, and they could do it by testing things over and over again. Put this much gunpowder in the cannon to see how far the ball goes. Right? Aiming downrange wasn't the issue. It was what angle do we put our cannon at, and how much gunpowder do we stick in there in order to have a lot of times those cannonballs weren't just cannonballs. They were themselves filled with explosives. So when they landed, they would make a big bang. But nevertheless, you want to be close to your enemy. You wanted that to land kind of on their heads. All right, so they had this problem of needing in the heat of battle to do rapid calculations, and Napier's bones solved that problem. What he did was realize that it's possible to add numbers with a couple of rulers. Well, wait a second. Let's see if we can think that one through. If you can add and subtract with rulers, you're halfway to using Napier's bones. Let's take a ruler like this. We'll think of one end of it as being 0, and every inch is a unit. 1, 2, 3, 4, Notice my ruler is only 6 inches long.
We get the idea.
All right. If I wanted to add 1 and 3, what I would do is take my second ruler and place it so that its beginning was at 1. So here's 0 on that ruler, and there's 1, 2, 3 on that ruler. So just move the base of the first ruler down to 1 on the top ruler, and then count down to the other number you're doing, and look above. So 1 plus 3 equals 2. You want to try a different sum? We can't do, let's do 2 plus 3. Let's make a new ruler picture. 0, 1, 2, 3, 4, 5, 6, 7. And if I put the second ruler at 2, 1, 2, 3, there's where 3 would be, here's where 2 is. What's this point right above 3? So we're seeing that 2 plus 3 is 5. Can you subtract like this? Yeah, well, you know, each one of these pictures is also a subtraction problem. I could view this as 4 minus 3 gives me 1. And this one is, I wrote a question mark there. What was this really? It's 5. 5 minus 3 gives you 2. So you can add and subtract with a pair of rulers. Not huge, but that's an interesting thing to note. The guy was looking for a mechanism, right? Something that's simple that soldiers could carry in the field to do these calculations with. Could you multiply with rulers?
I'm going to say no.
Well, not with regular rulers, but what Napier realized is you could make the scales on the rulers funny. He could adjust the scales so that, you know, basically, the beginning of, first of all, the beginning of the rulers will not be 0 anymore. It will be 1, because we're talking about multiplying. The reason these are 0 is that's the identity in adding. So we want the beginning of the ruler to be the identity for multiplying. We'll call that 1. But you want to have a setup that looks sort of like this if you're going to try to do multiplying. This end is 1, and 2 might be there. 3 will be a little closer, 4 a little closer. It kind of is a changing scale like that. So let me try to line up 2 rulers that have a multiplication problem on them. So this ruler would have 1, 2 would be right under 4, 3, 4. Well, let's look at what would be across from 3. Do you know what should be across from 3? If I put the beginning of this ruler at 1, at 2 rather, and this is 3, I'm hoping to get 2 times 3 right here. So this should be 6. And you see that if I continue this sort of shrinking pattern, I can make it be 6. 5 would be right in there. So his job now was to figure out how to make those divisions shrink, how to make these funny rulers. In fact, they were actually made with ivory. I've seen examples of these things in museums. There are lots of them at one time. So the soldiers now have a couple of sticks, and they just move them relative to one another, and they can multiply. What does subtraction do? If you've turned adding lengths into multiplying, what about subtracting? Why? I really wish I had the toys with me now, but I have a whole bag that I got on eBay of these things known as slide rules. In the day they called them slip sticks. They're basically Napier's bones grown up. They took the idea, it was just 2 pieces of ivory originally, but they took that idea and made them into these finely machined, beautiful aluminum tools that slide very finely, and you can work to about 3 decimal places of precision, adding and subtracting lengths, and actually affecting multiplications and divisions. Hidden Figures was one of the movies. Did anybody watch that? You watch that? Oh, it's going to be great. So, did they show slide rules in the movie? They should have. They showed the big computer, the big new computer that they were all using. Or the one woman at least was programming the computer. They haven't did anything with that computer. All the work back in the Apollo launches was with slide rules. The historically more accurate movie in that regard is what's it called? Apollo 13.
Never seen that.
It's a good movie. I mean, it takes a few, a little loose with reality in some cases. I mean, they make steering the lunar module look like it's a roller coaster ride at one point. You know, small little adjustments. Anyway, there's a point in that movie where the mission control guy, which I think was Gary Sinise, he yells, "Quick, I need a computer." Right? And you're expecting them to roll in the giant computer machine or something in that movie? It wasn't. It was a team of 3 people. Right? So there was a time when computer meant a person. That was their job type description, was to be a computer. And in NASA's case, they wanted a fail-safe computer. So they had 3 people run the same calculation, and then they checked one another. And if 2 out of 3 of them agreed, I think they usually said, "That's a go, you can go with that." But usually they want all 3 of them to agree on the computation. But those computers were using Sligo's. And they were using Napier's ones. So I guess we'll stop a little bit early today. I'll bring those with me next class and give you a little practice at using these kind of oddly distorted rulers where you add and subtract lengths like you end up multiplying them.
The big wonky calculator.
That's only for adding. That wouldn't do more complicated things than that. Those are literally called adders.
That's the only thing that like really starts
And
as,
hidden figures?
you know, like they were working with. It was an adding machine. I didn't realize it.
I think the machines, the tabletop machines here might have been like 4 functions. They certainly would have done like